And then cargo new, quest 2. I do want to add, I want to add this line. So let's go to quest 2 and say echo. Yep, I already had it. That makes it simple. Bacon, Clippy. Clippy is good because it's just hello world if I hit run. Yep, so that's good. Okay, so let's take a look at what quest 2 is all about. Everybody codes EOE quest 2. Oh, it's under solutions. That's right, quest 2. I don't know why I made a separate subdirectory for it, but I did. That's the way it goes sometimes. Okay, let's take a look here. Right, so we'd finished these these 3 steps, and I think I forgot to look at after we did part 1, but part 2, I think the letters were just a little bit dimmer. So I'm going to try to remember for quest 2 part 1 to take a look at what they are, assuming we can solve it. I have no idea if we can solve it. Quest 1 was harder than I thought it would be, given that this is, before I started it, I figured, this is just a fun little programming challenge that we could just bang out really quickly. But it turned out to use power mod, which is something that you don't use in the early stages of a programming challenge, at least not like Advent of Code wouldn't pull that out on day 1. And the Codicy or whatever they call it did not pull those kind of things out on day 1. So this seems like maybe, I don't know if they're meant to be all about the same level of difficulty or if this one's going to be even harder than this one. So enough preamble. I'm just stalling at this point because I don't know if I'm going to be able to solve this on stream. We'll see. Let's take a look at quest 2 of story number 1, Echoes of Enigmatus. Tangled trees. Well, this is new. I don't remember seeing these before. Okay. The story section, entry 31. The Tangled Trees Gambit. Finally, I've achieved a significant breakthrough after many sleepless nights and one unfortunate incident involving tea and a fire rune. Okay. I've created a new data structure worthy of the Order's archives, the Tangled Trees. Imagine 2 trees, not growing side by side, but tangled together like they've had a long and complicated argument. We plant each pair of nodes in parallel. Okay. They just threw out the word nodes there. I'm assuming we're talking about, program trees in software-based, like binary trees or multiple tuple trees. I don't know what you call trees with more than one. Anyway. Plant each pair of nodes in parallel. One is the left tree, one on the right. But, and here's a clever bit, they're not loyal. They can switch sides. Nodes can switch sides. Or trees can switch sides. Okay, yes, really. A node born on the left tree might wake up one day and think, today I feel like a right tree material. And off it goes. I'd say this behavior reflects real-life loyalty, confusion, and possibly bureaucracy. Some scholars claim it breaks the whole idea of structure. I'd say structure is overrated. Okay. Scribes refuse to index anything with it. They say it gives them migraines. The librarian threw a codex at me. Which librarian? Okay. The librarian. Okay, but I remain undeterred. One day the Order will thank me when our archives can finally reflect the shifting, tangled nature of meaning itself. Until then, I'll continue my noble quest and maybe even tangled heaps next. Wonderful. Maybe that tangled heaps will be part quest 3. Let's first build the trees without any swaps. Okay, so this is they're talking about taking a node from, so we have 2 different trees, 2 different, I don't know if they're binary yet. Let's assume they are. 2 different binary trees. And every so often you can swap nodes between the trees. But first we're going to build, okay, so part 1 is going to be, see if you can get your code up and running, right? So without any swaps. A command to add new nodes always has a unique identifier for the tangled pair. And 2 nodes, one for the left tree, one for the right. Okay. So every pair of nodes is going to have an ID. And eventually we'll swap them. A node is represented by a pair of values in the format rank symbol. Okay. The rank is an integer unique to both trees. Okay. And determines the tree's structure by indicating where the node should be added. The symbol can be any character and is used only for information. For example, symbols can hide a message within the tree structure. Okay. Maybe that's going to be our answer. Nodes are added to the trees following traditional binary tree rules. Okay. Namely, if tree is empty, node becomes a root. Otherwise, compare a new node's rank with the rank of the current node, starting from the root. The new node's rank is smaller, move left. Larger, move right. And repeat the process until an empty spot is found. And the fact that the integer is unique means it'll never be equal. So that's the good news. You don't have to worry about equality. Each tree left and right works independently, following the same rules. All right, so we're building up 2 trees. And I can see here we have a bunch of adds, but I guess we're going to do swaps at some point. Maybe that'll be part 2, it'll be swaps. And then what's part 3 going to be? Oh, no, the trees have 8 nodes hanging off of them. I don't know. Here's a process for building the trees while reading a list of commands line by line. Okay, so we have to go through line by line. That's what it's saying here. And we just add 10A to the left and 30H to the right. Okay, and then 15D to the left tree and 25I to the right tree. Okay, so and they're showing by the angle here whether it's a left or right. And this is interesting. They're actually growing up. Normally in textbooks, when they draw trees, they start with the root node at the top and they grow down, which is opposite of real life trees. But this is good. They're actually growing from the root up. All right, so I think I understand how this all works. This all makes sense to me. Finally, for each tree, identify the level with the most nodes. The level with the most nodes. A level represents all the nodes that are the same number. Oh, okay. Same number of steps away from the root. So this is level 0, level 1, and level 2. Okay, in the left tree, the level with most nodes is CFG, and the right, NLK. The final message is CFG, NLK. Got it. All right. And then we have a second example, which generates everybody codes. The name of the website. And then let's download our thing. Everybody codes E1Q02, and we'll put it here. Everybody codes E01, E1, Q02. That's interesting, is E, and then part 1. Okay. But you think, for story one, because these are the stories, not the events. Okay, I'm not going to worry about that part. I'm getting distracted. Let's see if we can figure out how to make a tree. And let's use this as our example, maybe. This will be our test code. And then see if we can come up with CFG, what was it? NLK. CFG NLK. All right. So Rust is notoriously difficult when it comes to making binary trees, because you have to wrap things in cells or options or something. Let's take a slightly less formal approach. Instead of using references for everything, we can just use a vec. So we're going to make a struct, I don't know what we call it, a vec tree. Sure, let's call it a vec tree, which has a vec in it, a vec of option of node. And what is a node? A node is going to have an ID, right? Because each one of them has its own unique ID, ID 4. Oh no, each pair has its own unique ID. So ID, I'm going to assume they're all U sizes. And then we're going to have a, was it rank and something? Rank and symbol. So let's have rank and a symbol, char. All right, so that's our node. Let's Let's derive display as well. Oh, no. I meant default. Debug derives a debug output, so that's all we need. So let's do this, and then maybe default for this as well. Okay. And I guess default is good enough because it looks like ID starts with 1. Let's take a look at our input. Yeah, it also starts ID 1. So ID 0 would be a good indication of it doesn't exist. So how do we add things to the tree? Impl vectree fn add. I guess yeah, default should just create an empty one. That's fine. So this will have a mutable reference to self and then a new node. And it doesn't need to return anything. We're just going to add it. So the idea here is we're going to start out, you know what we'll do is we will create a helper function called insert. So we'll say self insert node at level 0, starting at level 0. And that way we can do a recursive insertion. Insert, mute self, node, and then position usize. And it also returns nothing. All right, so we're going to look at the current position. What we'll do is say position start of search, and then position time. So we're going to start at 0, which means that left and right are going to be 1 and 2 in the vector. And then let's see, for node 1, its left and right are going to be 3 and 4. And then for node 2, the left and right, so let me draw that out. So say root 0, left of root is 1, right of root is 2, and then left for 1 is 3, and right for 1 is 4, and so on. So that's the way we're gonna do it. And it's basically we take the position, multiply by 2, and add 1. And that gets us our left and right. So so our left node is equal to pos times 2 plus 1, and our right node is pos times 2 plus 2. And that's how we're going to index into the array. All right. Now that I worked that out, we're going to say if the current length of the array self vec len, then we're going to resize the vec and then insert the position. So it's self vec resize width. And we have to give it a method. So pos plus 1. Oh, I can just say default. Okay. Right, and then we'll say self vec of pos is equal to node. And that's that. So that inserts it there. If the position is less than, then we might have if let some entry is equal to self vec get pos. Right? If we find an entry, then we want to compare the entry's rank. If entry rank is less than, oops, why is that green? Node rank. Why is that also green? Oh, because I didn't capitalize that. Okay. But that one's still, oh, that's an option. Right, because get returns an option, and I have options in there, so I have to say sum. Okay, that's better. Then what we'll do is we'll say insert, self insert node pos times 2 plus 1. We're going to insert on the left. Otherwise, if entry rank is greater than node rank, we'll insert on the right. Self insert node pos times 2 plus 2. Else we're going to panic. Node is equal to, is equal to entry. Right? Otherwise, if there's nothing there, then we can just insert it directly. Self vec pos equals node. Right? Because we could hit something that, because we've extended it, right? So it inserts a bunch of nones because there are options. There could be a none there, in which case we can just overwrite it. Expected option node found node. Okay, sum. And this also did the same thing here, sum. Okay. So that should allow us to do the inserts. What I haven't done yet is all the other code. Let's do all the other code. Let lines equals AOC lib read lines of everybody codes. And then what we're going to do is, this is going to be the annoying part, is parsing these things and generating all of this. Okay. For line in lines, we're going to take the line and split it. We have only adds for now. So I'll refactor this for part 2, because apparently there's going to be swaps in part 2, and there might be something even uglier in part 3. But for now, it's just going to be add. We'll split this into words. Line split by space. Collect vec. All right, and the words of 0 should be add. So words of 1 is going to contain the ID. Let underscore ID is equal to words 1 split once on equal sign. Let ID equals ID parse unwrap. Okay. And then left and right need to also be split up. Trying to think of, this is kind of annoying. Let's do it this way. I wonder if I can say left rank left symbol is equal to words of 2. And we're going to try this. Split once on open bracket, unwrap, dot 1, and that should give us 10 comma a close bracket. So then we'll say dot split once on close bracket dot unwrap dot 0 dot split once on comma unwrap. Wow, that's pretty ugly. Let's make a separate function for that, a little helper function. Rank and symbol line word string data entry. Let's just say s stir and returns a usize comma char. Right, that's all. That's what we care about is usize and char. So let's do this. Put that there. Let rank symbol equals this. And then we're going to say rank parse unwrap. And then symbol is, what is symbol? What type is that? Unknown. Oh, probably because I messed something up here. Oh, because I forgot to put the S in front. It's a stir. So we can just say symbol chars next unwrap. right? And then here we can just say rank and symbol of words 2. And then this would be right rank and right symbol. And this is word 3. Let's see if we actually got what we're looking for. Left rank, left symbol. And then right rank, right symbol. And we can just say, oh, it's not going to know the ID yet. So we'll just temporarily put this in here, I guess. Okay. Oh, I put an extra T on there. Oops. If I hit run, okay, so it is giving me output here. Oh, one of them is exclamation mark. Okay. Take a look. R, X, T, S, V, and we're going all the way down to Q and J. Yes. Okay. All 20. All right, so we're able to split everything up. What we want to do now is just create a node out of them. Impl node, fn new, ID usize, rank usize, symbol char, returning self, and this is self, ID rank and symbol. Right? So now we should be able to get rid of this. And we can say, oh, we need to create the left tree and right tree. Let mod left tree equals vec tree. And right tree is that. So now we're going to say left equals node new ID left rank left symbol. And so this, I should be able to say left, right, G. There, okay. And now we're going to say left tree, add left node, right tree, add right node. Okay. It ran. We're not using ID or symbol just yet, but we should have a tree at this point. Let's see if we can print it out, or print one of them out for node in left tree vec. We can just peek right in there. Node. Right? Yeah, some of them got to be none. This got put all the way down here for whatever reason, because that's the way things worked out. So I think we have a tree. What we should do is actually test it with the test input. Let's test it with the test input here, because that way we can see if this left tree looks the same as this guy. So let's grab this. Cat test 1.1 text. Right? So if we do that here, we should be able to compare it this way, right? So we have A is 10 is the first node. Then this should be 1 and 2, 15 and 5. Oh. I have these backwards. I have the comparison backwards. Yeah. Okay, that's an easy fix. Okay. 15 and 5. And then this is 1. So it should be 3 is 3 and C, yes. And 4 is empty, yep. This is 5 and 6 of 12 and 20. And then 7 should be empty, and it is, and 8 should be 4. Yeah. Okay, perfect. Okay, I think we're building the tree correctly. The next thing we need to do is find out the rank with the most number, a level, not the rank, the level, because these numbers are the ranks. We're looking for the level with the most nodes in it. So what we can do is traverse I know I'm already in one window, but why is this one smaller than it should be? Okay, I'm going to quit. I probably removed the code that makes it bigger, or move the hotkey that makes the window bigger. We're going to write a traversal. So we're going to traverse the tree, and we're going to grab all of the nodes from the tree and stick them in an array. So we'll have a vec per level, which contains a copy of, all we care about is the letters, right? The final message, yeah. So if all we care about is letters, we can just build up strings for each level. And if we do an in-order traversal, we should get it in this order. So we'll get a CFG from left tree and an NLK from the right tree. Okay, let's see if that works. So traverse. We're going to take a node, and we're going to take a starting position. And then we're also going to take a levels. And it's going to be a vec of string. Yeah. And we're going to, first we traverse the left, then we visit the current, the pause, and then we traverse the right. And that should give us what we need. We do need to know what depth we are. So let's create a function let's call it levels, which self, and it doesn't need anything else, and it just returns a vec of string. Right? And that way we can just call levels, and we don't have to worry about parameters and stuff like that, because we have to go self, traverse, position 0, depth 0. I got to add a depth here. And then a result, I guess. So we can say let mod result equals vec new. And this is just result. Right. Okay. That should do the trick. And then we can say if depth is greater than or equal to levels len, then we say levels. We're doing the same thing we did up here, right? Levels. This does need to be mutable reference. So we can modify it, resize with depth plus 1, default. All right, default string is whatever, and then we want to do that in the middle. Let's first we visit left, and then we do this. Okay, so we're going to say if. I'm trying to think about how we want to handle this case here, because we're going to use the get function to see if we have something. Let's write a little helper function here called has. Fn has self pause usize bool. And this is just going to say, is there an entry at this position? So if pause is less than self vec len and self vec pause is sum, then it has. Okay. So we're going to say if self has pause times 2 plus 1. If there's a left node, then we're going to visit it. Traverse pause times 2 plus 1, depth plus 1, and then levels. And then we do the same thing for the right side after we're done with the visit. So this is 2 plus 2, like that. Okay. I guess I needed to say like this. Yeah. It doesn't like this. Oh, could I put an if statement there that I don't need? There we go. Okay. So now we say if our depth is greater than what our levels can handle, then we extend the levels array, and then we're going to say levels of depth dot push. Right, we're just going to add to that string what's currently there, self vec of pos dot symbol. Oop, it doesn't like that. Why not? Oh, because I have to unwrap as symbol. There we go. Ooh, cannot move out of index. Oh, I guess we do as ref. Like it suggests. There, okay. So now we're not calling it yet. Let's call it. So instead of printing out this business, what we'll do is we'll say, what did I call it? Levels. So we'll just say left equals left tree levels, and right is right tree levels. And we can just print those out for now and see what they look like. Okay, so we can actually see which one's the longest. We do have CFG and we have NLK. So how do we find the longest one? It should be easy enough, right? I guess we could max by len. Iter max by s len unwrap. AB. So this would be a.len.cmp b.len. No, it doesn't like that either. Oh, okay. Yeah, then we get CFG, and we can do the same thing for the right tree now. Actually, you could just do this, right? CFG NLK, and now I just need to print them out, right? So I can just say part 1 is equal to, oh, that's right, that was the other thing. This is quest 2. Quest 2, and what is the quest called? We got to do this right. Tangled trees. And it's just, all we do is print out left, right. There we go. We're not using ID yet, so let's just change that really quickly. So at least it's clean, and I'm sure we'll use that in part 2 or part 3 or whichever. And now I think we can try it on our real code. And we get quack bang mjrjsmmt. Let's see if that is the answer. Nothing can crack you down. All right, that's the right answer. Global place 56. And apparently it took me 32 minutes and 23 seconds.